China is building something that has never existed before. I want to explain exactly what it is, how it works, and what it actually means for the world. Not in vague terms. In real numbers, real steps, real consequences. The project is called Medog. It is a hydropower complex on the Yarlung-Tsangpo River in Tibet. When it is finished, it will produce 60 gigawatts of electricity. That number is confirmed in Chinese state engineering documents and publicly reported by multiple international outlets. 60 gigawatts. I want to make sure that lands properly. The Three Gorges Dam in China has been the world's most powerful dam since it was completed. It produces 22.5 gigawatts. Medog will produce nearly 3 times that amount, from one river, in one canyon. This is not a modest upgrade. This is a completely different category of power generation. Nothing built by any country in human history produces more electricity from a single river system. That is the starting fact. Everything else builds on it. Now let me explain why this particular river, in this particular place, makes this possible. The Yarlung-Tsangpo runs through what is confirmed to be the deepest canyon on Earth. Deeper than the Grand Canyon. Deeper than any other river canyon on the planet. The river drops 2,000 meters in just 50 kilometers. I want you to think about what that means physically. The river is essentially falling off a long cliff in slow motion. That drop is energy, pure gravitational energy. Every meter of drop that water makes can be converted into electricity if you have the right machines in the right place. Engineers have been looking at this canyon for decades, knowing what was there. The drop is so extreme, and the water volume so large, that the energy potential is almost impossible to match anywhere else on Earth. That is why this site. That is why this cost. That is why this difficulty. Because there is nowhere else on Earth where you get this much gravity and this much water in the same place. The canyon sits at the eastern edge of the Himalayas, in a remote part of Tibet called Motuo, also written as Medog. The river makes a massive U-shaped turn around a mountain called Namcha Barwa. That peak stands at 7,700 meters above sea level. This bend is called the Great Bend. The drop happens right here, concentrated in this short stretch where the river swings around the mountain and falls steeply into lower terrain. China broke ground on this project on July 19th, 2025. The target completion date is 2033. The cost is $167 billion US dollars. Those 3 numbers, the date, the deadline, the cost, are all confirmed from official announcements. What I find genuinely hard to wrap my head around is not just the scale of what is being built. It is the scale of what had to happen before building could even start. Let me explain that first, because without it, the construction itself makes no sense. This canyon is one of the most remote places on Earth. There were no roads into the deep canyon sections, no infrastructure, nothing. The Medog Highway only opened in 2022. That single road is the only land connection into the region. Before any dam could be poured, before any machine could turn, the site had to become reachable. This required a construction program that would itself be a major project in any other country. New access roads were blasted directly out of the canyon walls. 6 new bridges were built just to reach the first dam location. A cable car system was installed across the main gorge, so workers could cross in 8 minutes instead of 3 hours by road. At the deepest and most vertical canyon positions where even the new roads could not reach, heavy lift helicopters were used. Precision equipment, emergency parts, anything time sensitive, all flown in. The logistics network required before construction, just the access system, cost billions of dollars on its own. 40 million tons of cement need to reach this site. Millions of tons of steel, all of it coming through that one highway, then through the new access roads. I find this detail important because it tells you something real about the ambition here. When you have to spend billions just making a place reachable before you start the actual project, you are operating in a completely different league of engineering challenge. Site power also had to come first. The machines that build the dam need electricity before the dam exists to make electricity. Power lines were run along the highway route before construction equipment arrived. Road first, power line second, worker camps third. Then the machines came. That sequence matters. It shows how methodical the planning had to be. You cannot rush the order. Once the site was reachable and powered, the next problem was the river itself. You cannot build a dam in a river. The river is in the way. The Yarlung Tsangpo runs at 14,000 cubic meters per second during monsoon season. That is an enormous amount of moving water. And the solution is a diversion channel. Engineers blasted a new channel through the canyon wall to give the river a temporary path while the construction happens in the original riverbed. The rock being blasted is Cambrian granite, confirmed to be around 200 million years old. A section of canyon wall was demolished in a controlled blast in approximately 4 seconds. Then, excavators and dump trucks cleared the debris. The temporary new channel was shaped. Then, a cofferdam was built upstream. A cofferdam is a temporary barrier that pushes the river into the new channel. It is built from rockfill with a clay core to stop leaks. This cofferdam costs hundreds of millions to build. When the main dam is finished, the cofferdam gets demolished. It is a single-use tool. That detail impressed me. Hundreds of millions of dollars spent on something designed to be destroyed. That is how serious the engineering requirements are here. With the river moved, workers could walk into the dry riverbed for the first time. The foundation rock was exposed. Every loose fragment was removed. Holes were drilled into the rock and logged. Every meter of rock described and recorded before any concrete was poured. Then cement grout was injected at high pressure into every crack and fracture in the granite below the dam footprint. The goal is to seal every possible water path under the dam permanently. No leaks under, No leaks through. The foundation has to be perfect because once the dam is complete, no one gets back to that rock. Ever. Now let me explain the tunnel system, because the tunnels are the core of how this dam actually works, and they are also one of the most technically difficult parts of the entire project. There are 4 tunnels. Each one is 20 kilometers long. They go straight through the Namcha Barwa mountain, not around it. Through it. 7,700 meters of granite above the workers boring these tunnels. The tunnels carry water from the reservoir at the top of the drop down to the powerhouses at the bottom. Water travels through these tunnels at 60 meters per second. That speed is what drives the turbines. To bore the tunnels, China used tunnel boring machines, TBMs. Each TBM is 14 meters in diameter. That is roughly the width of a 4-lane motorway. Each machine weighs 4,000 tons and was delivered to the site in 300 separate pieces. Assembly of each machine took 4 months on site. The cutting face of each machine has 240 disc cutters. Each cutter is made from tungsten carbide, one of the hardest manufactured materials in existence. 4 of these machines ran simultaneously, boring from opposite ends of the mountain, 24 hours a day, 7 days a week. Workers operated in 12-hour shifts inside the tunnel, hot, loud, the mountain pressing from every direction. 20 kilometers ahead of where they stood was daylight. As each TBM moved forward, precast concrete rings were installed behind it to hold the tunnel open. Each ring is made of 9 segments plus 1 locking piece. At full speed, 1 ring was placed every 40 minutes. 50,000 cubic meters of granite were removed per tunnel. That excavated rock was used as fill material for the access roads outside the mountain. Even the waste material had a use. At roughly kilometer 8 of each tunnel, groundwater became a problem. This is confirmed to be a standard challenge in Himalayan tunneling. The rock is fractured. When the TBM opens new cracks, water finds them instantly. The solution is cement grout injected under 50 bar of pressure, that is high pressure, into the fractured zone. Wait 48 hours. If the grout holds, boring continues. If not, more grout. There is no shortcut. The mountain decides the pace. Each tunnel took 51 months to complete. 4 tunnels. That is the answer to the question of how long it takes to bore. 20 kilometers through the Himalaya. Seismic sensors were installed every 100 meters inside every tunnel. The Himalayas are one of the most seismically active regions on Earth. The sensors detect movement before any human can. If the mountain moves, work stops. When it settles, work resumes. The sensors are not optional. They are what keep 800 workers per site alive. Steel penstock pipes were installed through the finished concrete-lined tunnels. These are the pipes water actually flows through at 60 meters per second. Intake gates were fitted at the river end of every tunnel. These gates control how much water enters each penstock. They are the first control point in the entire system. Now the dams themselves. There are 5, not 1. 5 dams in a chain across 50 kilometers of canyon. This is called a cascade system. Each dam sits downstream of the previous one. The river drops in stages through all 5. The total 2,000-meter drop is shared across the chain. The design is important because no single dam wall could capture the entire drop in one step. The rock, the canyon geometry, and the physics of dam engineering make a cascade the only viable approach for this site. The dam walls are built using roller-compacted concrete. This is a specific method. The concrete mix is drier and stiffer than normal concrete. It gets delivered by dump trucks and spread in layers, 300 millimeters thick. Then, a heavy vibratory roller compacts each layer immediately. The next layer goes on before the previous one fully sets, which bonds them together. No large formwork frames needed. This method is faster than conventional concrete pouring. But temperature is a problem. Concrete generates heat when it sets. Too much heat causes cracks. Cooling pipes are run through the dam body during construction. Cold water circulates through the pipes to carry heat away. Every layer of completed concrete is core sampled and tested for density and strength. If a layer fails the test, it gets demolished and recast. No exceptions. The canyon walls on both sides are vertical. The dam wall rises between them. 5 dam walls, 5 simultaneous operations, 1 shared deadline. The spillway gates deserve a specific mention. These are the emergency release valves built into each dam. They exist to handle the most extreme monsoon the Himalayas can produce. Each gate weighs 900 tons. They are installed by crane in one single lift. If a gate does not seat correctly in that one lift, there is no room in that canyon to reposition and try again. Everything about this project has that quality. One chance, no margin for error, because the location allows for nothing else. The powerhouses sit at the base of each cascade. Each powerhouse has 12 turbines, 5 powerhouses, 60 turbines total across the system. Each turbine pit is 12 meters in diameter. Each turbine is rated at 1,000 megawatts. One turbine equals one large power station. There are 60 of them, 12 per hall, 12,000 megawatts per station. 5 stations. The math produces 60 gigawatts total when all 60 turbines run simultaneously. The turbines are Francis turbines, a confirmed design standard for large hydropower. These are the largest Francis turbines ever manufactured. Each runner, which is the spinning part the water hits, weighs 280 tons. They were made in Harbin, China. Each one was shipped by heavy rail from Harbin to Lhasa, then road freight for the final 500 kilometers into the canyon. 3 months per unit, per journey. 60 units. That is 180 months of combined transport time for the runners alone, across the whole fleet. The runner goes into the pit by overhead crane. Alignment is checked to hundredths of a millimeter. A runner that is even slightly misaligned will destroy itself in hours once it reaches operating speed. Above the runner sits the generator stator. The rotor, connected to the runner, spins inside the stator, moving magnetic field, electrical current induced, electricity produced. Every winding connection in the generator is measured for resistance before the generator housing is closed around it. Once closed, it cannot be easily reopened. So every measurement has to be correct the first time. What I find particularly interesting about the electrical side of this project is the voltage required to move the electricity from this canyon to where it is needed. The generators produce electricity at a relatively low voltage. Step-up transformers outside each powerhouse raise that voltage to 800,000 volts for long-distance transmission. 800,000 volts is too dangerous to manage with outdoor switchgear in a narrow Himalayan canyon. So gas-insulated switchgear is used instead. It is fully enclosed. It works in the confined canyon space. 800,000 volt transmission towers are constructed from the canyon rim. The electricity leaves Tibet and travels approximately 4,000 kilometers to eastern China. Converter stations in Sichuan and Yunnan provinces convert the power from DC back to AC. It enters the national grid there. The entire journey from turbine to grid happens in milliseconds. 60 gigawatts arriving in eastern China from a canyon most people in that country have never visited. A centralized control room monitors all 5 stations simultaneously. One operator at one desk can manage all 60 turbines. This level of automation is standard for modern large-scale power infrastructure, but the scale here is confirmed to be without precedent in hydropower specifically. Now I need to explain what happens to the water after it passes through the turbines, because this is the part that directly connects to the 300 million people downstream. And this part is critically important. Water enters the intake gate, falls through the penstock at 60 meters per second, hits the turbine runner, spins it, then exits through a draft tube below the runner. This slows the water down. The energy has been removed. Then tail race tunnels carry that water back into the river channel downstream of each dam. The volume of water that entered the intake is the same volume that exits into the river. The water is not consumed. It is not stored permanently. It passes through the system and continues downstream. China's engineers confirm this. The phrase used is accurate. They are borrowing the drop, not taking the water. But here is where I need to be honest about the complexity. The volume returning to the river may be the same, but timing is not the same. A dam can hold water back during dry season and release it during monsoon, or hold water back during monsoon and release during dry season, or hold indefinitely. The timing and volume of releases at any moment is a decision made by whoever controls the dam, and China controls these dams. That is the confirmed fact, and the river downstream of these dams becomes the Brahmaputra in India, then the Jamuna in Bangladesh. This is confirmed geography that has been publicly reported for decades. The Yarlung Tsangpo, the Brahmaputra, and the Jamuna are the same river at different points in its journey. The river does not know it is crossing borders, but the people living along it do. 30 million people in Assam, India alone depend on this river. Confirmed figure from Indian government demographic data. Across India and Bangladesh combined, the estimate is 300 million people. That number covers drinking water, irrigation, fishing, and daily life for hundreds of millions of people. And every one of those people is now downstream of 5 dams they did not vote on, were not consulted about, and are not party to any treaty covering. This is confirmed. There is no water-sharing treaty between China and India specifically covering the Yarlung-Tsangpo and Brahmaputra system. India's External Affairs Minister Jaishankar raised this directly at an international meeting in July 2025, the same month China broke ground at Medog. The concern raised was not that China would take the water. The concern is about control of timing and flow. A flood held during monsoon protects Indian cities. A flood released at the wrong time damages them. A hold during dry season means drought for downstream farmers. A release during dry season helps crops. Every one of those decisions is made in Beijing. The people affected are in Assam, Arunachal Pradesh, and Bangladesh. No framework currently covers what happens when those decisions create conflict. To me, this is not a minor diplomatic issue. This is 300 million people with no formal protection over a resource they depend on every day. There is also a longer-term dimension I think is worth understanding. The Yarlung Tsangpo is fed significantly by Tibetan glaciers. As those glaciers shrink due to confirmed climate change, the long-term water volume in the river will change. A dam system built for current flow volumes may operate differently as glacier melt, shifts the seasonal pattern of the river over the coming decades. This is not speculation about whether climate change is real. It is confirmed. The question of how it interacts with this specific dam system over a 50-year operating lifetime is something current models are still working through. Let me also put the clean energy side in fair context, because it matters. 60 gigawatts of electricity with no coal and no carbon emissions is a real and significant benefit. China burns enormous amounts of coal for electricity. Every gigawatt replaced by clean hydropower reduces coal burning. The confirmed plan is for Medog electricity to power the equivalent of 300 million Chinese homes. That is a real reduction in carbon emissions at a real scale. I do not think this point should be dismissed. Clean electricity at this scale genuinely matters for climate. The engineering that makes it possible is remarkable. The problem is that the benefits flow to one country while the risks are distributed across 3. That imbalance is the core geopolitical issue, and it is currently unresolved. But the river keeps flowing. It does not stop at the dam. It does not stop at the border. 25 kilometers from the last powerhouse, India begins. The same canyon, the same water. A different country with no control over what was built upstream of it. Bangladesh is further downstream still. The Jamuna arrives in Bangladesh after crossing the entirety of India. Whatever flow pattern China sets at Medog, Bangladesh receives the final result of that pattern last. With the least political leverage of the 3 countries and the most dependence on the river's seasonal regularity. So for me, the main thing I take from all of this is simple. Medog is 2 records at once, the biggest power station ever built, and the largest unresolved water rights situation on Earth. Both of those things will be true in 2033, when the last turbine spins up. The electricity is real. The river is real. The 300 million people are real. And right now, only one of the three countries involved gets to decide what happens next.